in the last couple of videos, we saw that we can describe a curve by a position vector valued function. And in very general terms, it would be the x position as a function of time times the unit vector in the horizontal direction, plus the y position as a function of time times the unit vector in the vertical direction. And this will essentially describe this, if you can imagine a particle, and let's say the parameter t represents time, it'll describe where the particle is at any given time. And if we wanted a particular curve, we can say, well, this only applies for, let's say for some curve, we're dealing, it's r of t, and it's only applicable between t being greater than a and less than b. And that would describe some curve in 2 dimensions. We can just draw it here. This is all a review of really the last 2 videos. So this curve, it might look something like that, where this is where t is equal to a, that's where t is equal to b, and when, so r of a will be this vector right here that ends at that point, and then as t, or if you can imagine the parameter being time, it doesn't have to be time, but that's a convenient one to visualize. Each corresponding as t gets larger and larger, we're specifying different points on the path. We saw that 2 videos ago. And in the last video, we thought about, well, what does it mean to take the derivative of a vector valued function? And we came up with this idea that, and it wasn't an idea, we actually showed it to be true. We came up with a definition, really, that the derivative, I could call it r prime of t, and it's going to be a vector. The derivative of a vector valued function is once again going to be a derivative, but it was equal to, the way we defined it, x prime of t times I plus y prime of t times j. Or another way to write that, and I'll just write all the different ways just so you get familiar with, dr dt is equal to dx dt. This is just a standard derivative. X of t is a scalar function, so this is a standard derivative, times I plus dy dt times j. And if we wanted to think about the differential, one thing that we can think about, and whenever I do the math with the differential, it's a little bit hand wavy. I'm not being very rigorous, but if you imagine multiplying both sides of this equation by a very small dt, or this exact dt, you would get dr is equal to, I'll just leave it like this, dx dt times dt. I could make these cancel out, but I'll just write it like this first, times the unit vector I plus dy dt times the unit vector times dt times the unit vector j. Or we could rewrite this, and I'm just rewriting it in all of the different ways that one can rewrite it. You could also write this as dr is equal to x prime of t dt times the unit vector I. Sorry, this was x prime of t dt, right? This is x prime of t right there, times the unit vector I, plus y prime of t, that's just that right there, times dt times the unit vector j. And just to, I guess, complete the trifecta, the other way that we could write this is that dr is equal to, if we just allowed these to cancel out, then we get is equal to dx times I plus dy times dy times j. And that actually makes a lot of intuitive sense, that if I look at any dr, so let's say I look at the change between this vector and this vector, let's say the super small change right there, that is our dr, and it's made up of, it's our dx, our change in x, is that right there. You can imagine it's that right there, times, but we're vectorizing it by multiplying it by the unit vector in the horizontal direction, plus dy times the unit vector in the vertical direction. So when you multiply this distance times the unit vector, you're essentially getting this vector. You're essentially getting this vector right here. And when you multiply this guy, and actually our change in y here is negative, you're going to get this vector right here. So when you add those together, you get your change in your actual position vector. So that was all a little bit of background, and this might be somewhat useful in a future video from now. And actually, I'm gonna leave it there, because I just wanted to introduce this notation and get you familiar with it. In the next video, what I'm going to do is give you a little bit more intuition for what exactly what exactly does this thing mean? And how does it change depending on different parameterizations? And I'll do it with two different parameterizations for the same curve.